Let's start some numericals on waves in strings. The first question is on the screen. String of length 100 cm and has a mass of 100 gram. If the tension is 20 Newton, what is the velocity of transverse wave in the string? So here, the given quantities are length of the string is 100 cm, that is 1 meter. Mass of the string is 100 gram, that is 0.1 kg. So mass per unit length will be mass by length is equal to 0.1 by 1, 0.1 kg per meter. Now we need to calculate the transverse tension is given as 20 Newton. We need to calculate the velocity of transverse wave. The formula for velocity of transverse wave is root under T by mu. So equal to 20 by 0 0.1 root under 20. So 200 point the answer for this question. Then our next question is on the screen. A wire of length 10 cm and radius 0.5 mm is stretched with a weight of 4 kg. Find the frequency of the fundamental load produced by it. Density of the material of the wire is given as 8500 kg per meter cube. So our solution is length is given as 10 cm, that is 0.1 meter. Radius of the wire is 0.5 mm. This is equal to 0.5 into 10 power minus 3 meter. Mass is 4 kg. The density of the material is given as 8500 kg per meter cube. So first we need to calculate area of cross section of the wire. First we will calculate area of cross section wire. For example, if this is the wire, the cross section, we need to calculate this cross section as pi r is 3.5 into 0.5 into 10 power minus 3 whole square, whose value is equal to 7.85 into 10 power minus 7 meter square. And finally we get the formula for frequency fundamental load as 1 by 2L root E by mu. Mu is mass per unit length, but we cannot calculate the value of mu because mass of the wire is not given. Rather we have got the weight that has been hanged on the wire. So this weight gives the tension produced in the wire as mg equal to 4 into 10 40 Newton. But for mu we need mass of the wire, which is not given. So for that we will modify this formula as 1 by 2L root under E by density into area. Actually, mass per unit length is equal to density into cross section area. Now all these values are given. We can now calculate our value. 2 into 0 0.2 root under 40 by 85 into area 7.85 into 10 power minus 7. Value is as 387.03 387.03 hertz. This is the answer for this question. Second question. Third question is on the screen. A wire under tension vibrates with a fundamental frequency of 240 hertz. What would be the fundamental frequency if the wire were half as long, twice as thick, and one under one fourth of the tension? So here two conditions are given. First, initial, then in the initial condition, if we consider length of the wire as L, uh, tension thickness of the wire as R, and tension of the wire as T. Then final condition, the length is L dash equal to L dash equal to half of initial length. Similarly, thickness is equal to R dash, which is twice as initial thickness. Similarly, tension on the wire is T dash, which is equal to 1/4 of the initial tension. Now, in the initial condition, the frequency, fundamental frequency, value of fundamental frequency is equal to 240 hertz. We need to find the fundamental frequency for final condition. Here, formula for fundamental frequency will be equal to 2 L dash 2 dash by density into A dash. Density is same for the final condition because the wire is same, so density will be same. Only length, tension, and area will be different. We will convert them to their initial values. L by 2 P by 4 into density, and area is equal to pi r square, so pi r dash square, and we will put the value of r dash equal to 1 by e pi density. R dash is 2r square. Finally, this becomes 1 by 2l root on t by into 2 into 1 by root on t by density into initial area into 1 by 2, and the value of the term in the bracket is given here. So this is equal to t This is the answer for the third question. Fourth question is on the screen. A piano string has a length of 1 meter, uh, and density as 8,000 kg per meter cube. What is the when the tension on of the string produces a strain on the wire is 1%, that is 1 by 100, that is 0.01. The fundamental note emitted by the transverse vibration is fundamental frequency is 340 hertz. Calculate the Young's modulus. Young's modulus is equal to. So now we'll use the formula for fundamental frequency as 1 by 2L root under P by density into area. Fundamental frequency is 340 equal to 1 by 2 into 1 under P by density of density is given. So 8,000 into area. From this we will calculate the value of P by A. P by A into 1 by 8. Then finally the value of T by A comes to be 3.69 into 10 power 9 Newton per meter. Now we calculate this is stress. Tension by area is equal to stress. So we need to calculate Young's modulus is equal to stress by strain is 3.69 into 10 power 9 by 0.01. Value of strain is 0.1. So 3.611. That is the answer for fourth question. Last question is on the screen. A wire of mass 0.5 gram and length 37.5 cm is making 256 vibrations per second. The tension supplied by a brass weight hanging vertically. When the weight is immersed into water, the vibrating length of the wire is shortened by 5 cm to regain its original pitch. What is the density of the brass? So here a brass weight hanging on the wire gives tension. First it was in air and after then it was in water. So we will let weight of the brass weight in air as WA. This is also equal to tension in air, and similarly weight of the brass weight in water as WL. Weight in water, this is also equal to tension in the liquid. Now when the weight was in air, when the brass weight was hanged vertically in the wire in air, at that time the length of the wire is taken as 37.5 cm or 0.375 meter to have the frequency, fundamental frequency as 256 vibration per second, and mass of the wire is 0.5 gram, that is 0.5 into 10 power minus 3 kg. In the second case, when the weight was in water, in that time, to have the same frequency 256 hertz, the length of the wire was shortened by 5 cm. That means now the length is 32.5 cm, that is 0.325 cm. In this case, mass of the wire will also decrease, but better we use the value of mu. The value of mu in both the cases will be same. We don't know the mass of the wire when the weight was in air, but we can calculate the mu in case of air, and the value of mu in air will be equal to mu in water. 0.37 of mu is 1.33 into 10 power minus 3. The value of mu will be same. Now we'll simply use formula for both the cases. The fundamental frequency is 1 by 2L root T by T by mu for the air, and similarly for the weight in water by 2L dash under T dash by mu. Mu is same in both the cases. Tension is equal to weight. Okay. Now we equalize both of these cases. Equalize of these cases 1 by 2L by mu is equal to S equal by mu. Since frequencies both in the same cases, mu is also same. Also same. Here we can get L dash by L is weight in liquid by weight in air. So length in is 0.325. Length in air is finally weight in liquid by weight in air is 3.5 where 0.71. Use the concept weight of the brass weight in air is in liquid is equal to weight in air minus weight in 0. Weight in air is volume into density of the material into G minus thrust as volume into density of the water into G, and this is volume intensity of the material into G is equal to 0.751, and this becomes density of the material minus density of water by density of mercury 0.751. Then calculated density of material minus density of mercury water as 1000. 0.751 density of the material 49 density of the material is equal to density of the material to then 16.2 AC this